Good afternoon, everybody. For those of you who do not know me, my name is Ali Kujuri. I'm an adjunct professor at the Department of Engineering Science and one of the organizers of this lecture series. First, I would like to thank Mr. Sharon Marivani and Ms. Kate Laff, who helped me in organizing this series. On behalf of the department, that's the Engineering Science Department and the School of Science and Technology, let me thank you all to be attending now this 8th lecture in this academic year, and in fact the 149th lecture in this series since we started in 2006. Before I introduce our guest speaker for today, let me mention that delicious pizza will arrive at 5:30 right after the lecture. And our next lecture will be on October the 3rd, titled Machine Learning by Dr. Shahzad Jamshidi. He's a data scientist in REMI Pty, Australia. Our guest speaker is Dr. Sebastian Gomez Diaz, and the title of his talk is Non-Reciprocal Manipulation of Electromagnetic Waves. Dr. Gomez Diaz is an assistant professor in electrical engineering and computer engineering, UC Davis. He received his PhD degree in electrical engineering from the Technical University in Cartagena in Spain in 2011. From October 2011 to March 2014, he was a postdoctoral fellow at École Polytechnique Fédérale de Lausanne, Switzerland. Then, from May 2014 to 2016, he continued his postdoctoral work in metamaterials and plasmonic research laboratory of the University of Texas at Austin, Texas. He has received several recognition, including the NSF Carrier Award in 2018 and Leopold Felsen Award for Excellence in Electromagnetics in 2017. His main research interests include multidisciplinary areas of electromagnetic and wave propagation and radiation, metamaterials and metasurfaces, plasmonics, two-dimensional materials, non-linear and non-reciprocal phenomena, and other emerging topics on applied electromagnetics and nanotechnology. So here is Dr. Gomez Diaz.
Thank you very much, Dr. Kujuri, for this very nice introduction. So, thank you all for coming here. My name is Sebastian. I'm assistant professor at UC Davis. And I'd like to talk today about what the type of research lines that we're working in my research group. So most of the things that I'm going to be working here has actually been done by my students. So I'm just trying to help them around. And I also want to make this talk pretty interactive. So if you have any question, any curiosity at any time, please stop me and I'll be very happy to talk or try to clarify any questions you may have. So what we're trying to do in my research group, one of the major research lines, is to control and manipulate non-reciprocity. What is that? So first, is like, why are we doing this? What is our goal? So, for instance, right now, most of the communication systems, they are not full duplex. It means that you are transmitted at one frequency and you're receiving at a different one. All of you have a smartphone. In your smartphone, you have one antenna operating at one frequency to transmit and a different one to receive. That's why, because you cannot integrate a circulator to isolate these two antennas, because it requires a magnetic field. So that means that we are wasting a lot of electromagnetic spectrum. We are not achieving full duplex communication. And also when you are having like more powerful radars, there is also a lot of crosstalk between antennas. And if we go like towards the very big picture, we are coming into a more modern and interconnected world and life where we're going to have electromagnetic waves everywhere surrounding us. And is the way that we control and we can interact with the electromagnetic wave is going to define the functionalities, the data rate, the connectivity that we have. Not only for our smartphone, but for satellite communication, for sensing, for detection, for inter-chip communication, everything. So what we're trying to do is to have a better control of this electromagnetic wave in ways that so far are not possible. And wave can be in a broader spectrum. We can talk about radio wave, that they are like, the wavelength is very large, or we can go to optics and photonics, where the wavelength is really short. So in the particular aspect that I'm going to be talking today is about reciprocity. What does it mean? Well, it means most likely that in regular media, if I'm able to see you, you're going to be able to see me. So this medium is reciprocal. That's good, but imagine that you have a very powerful laser and you got a reflection somewhere, the energy is going to go into the laser. Most likely that laser is going to be broken because you're going to burn it. Or if you have an antenna system and you want to transmit, but if you are receiving energy, then you need to go this with this circulator, otherwise you're going to cancel, you're going to have a very strong interference. Or for instance, if you have a primary radar system, when basically you send some energy, it's going to be reflected in the object that you want to detect, and that's the way a radar system. If you have a lot of interference nearby, you're not going to be able to detect that signal. Or if you have a jamming signal, someone that really wants to disturb your communication system is going to be able to put a lot of power here, and that's going to block your device. Or if you have an antenna in top of a roof where there are like hundreds of antennas, they are going to interact with each other, and maybe you are going to be able to transmit, but you're going to have a lot of cross-coupling. So there are like many ways where it is very important to be able to transmit from A to B and not to receive from B to A, or at least to tame or control that, not let it to be something fixed. So what we want to do is to control and manipulate that. So that's going to be the major motivation of my talk. How can we do that? What are the normal ways to break reciprocity? For many years, people have been using magnetic fields. So you know that you apply a static magnet, and then you align all of the electrons that are spinning in the atoms along one particular direction, and that works pretty well. They work really nice, and we have like all of the circulator, all radars, most of components, they have magnetic materials over there. But we have a major problem. It's like you cannot put these magneto-optical materials in your smartphone. You cannot integrate, you cannot miniaturize, because they are not compatible with integrated circuits. So one of the major goals in the recent years in the literature or in the community is trying to find ways to do what the magnets are doing without any magnet. How can we do that? Well, in order to get this integration thing, one option was to use direct current using transistors. That it was working relatively well, but they have a problem with power handling. The amount of power that this approach was able to handle was little, and then for many situations it was not working good enough. Then another option is to use nonlinear media. So if you have a medium that interact with wave in a nonlinear fashion, that means that you can create double frequencies, and you can, as a function of the power that you are pumping into the system, this medium is going to behave differently. And that was a very nice solution, trying to control how this nonlinear medium responds. But one of the major problems is like, if you are feeding the system from both sides at the same time, then since you are pumping a lot of power, the system is going to doesn't know what to do, and you are going to get somehow an unknown answer. And very recently, there is like a lot of trend in what it is a linear or angular momentum. And in order to explain this concept, I like to just put this image. So the origin of this concept was, apart from some theoretical works from some years ago, was something very simple that happened when I was doing my postdoc in Austin. Is like they wanted to do a circulator in acoustics, because there were no circulator for acoustics. So it's just a pressure wave. So what this guy did, one of my friends, one friend that now is professor in Europe, is like he put 3 CPU fans that cost him like $5, 10, and he put inside of this ring and then made the air flow. So the air was moving inside. What happened? So when the voice came here, it just got locked to the movement of the air and just follow the flow. That was the cover of Science, and that was really, I was there and I was holding that thing in my hand. I was, oh, come on guys, that doesn't look so difficult. I should have had this idea. But this has much stronger implications. It's like, if we can make something as if it is moving, we can control the way that this wave in general, it could be acoustic, thermal, electromagnetic, any type of wave, in ways that before they were not possible. And that's why many people are working on this way. And one of the next directions was to create the same circulator that was doing before with magnets. Now they were trying to mimic this concept, like making the air move. How can you do that? Well, they were saying, we cannot make the air flow, but we can put here varactors or capacitors that they're going to change with time, and it's going to make like you have permittivity or some material that appears that is moving, but it's not moving. So you are just changing how these varactors changes with time. And that gives rise to the first magnetless circulator that could actually be integrated in your phone. And I know many people are working into that direction. And this is something that I like very much, how you can have some nice concept from acoustics, and then you can borrow and apply to electromagnetics. And then I know some people now that they're using this to thermodynamics, and you can borrow from one topic, from one field, and apply it to a different one. And it's pretty, you can learn a lot from all of these things. So many recent works are going in this direction, and of course, with some people working on that, they came up with a very smart ways to modulate all of these varactors and capacitors in order to reduce the loss, increase the isolation between the different ports of the circulator, and there have been CMOS implementations of that. And in all cases, there is always the same goal: build circulators that could be integrated in your smartphone without magnets. So this is like how the state of the art is going through the past year. So what are we doing in my group? Well, in my research group, we are going into something, we are starting from that, and we are trying to go a little bit to extend this concept to a much more broader aspect. So we want to control electromagnetic wave breaking reciprocity and apply it to a wide variety of devices. So circulator has already been done, but if we are staying, for instance, at microwave, we can make metasurfaces that can interact with light in one way, but if the light is coming from this direction, it's gonna go somewhere else. So you can have lenses that focusing in one direction, but not in the other one. Or you can have phase array antennas, some antennas that are able to radiate, but not to transmit. Or I'm able to radiate in one direction and to receive in a different one. So you can have much more functionalities. Or you can have filters that you have a bandpass filter along one direction from the same device, and on the other direction you have an isolator. This is like the first block that I would like to talk about microwave, and those devices could be relatively simple. There are like simple PCBs that can be fabricated pretty easily. And the second block is like, how can we push technology and going a little bit higher in frequency? We can go as the communication data rates are increasing, and we need more data. People are pushing up in the frequency range. So there is a lot of communications at terahertz and infrared frequencies, and there is like these novel 2D materials like graphene, like black phosphorus, hexagonal boron nitride, that they have new properties. So in this block, I'm gonna tell you like what are the latest research efforts that we're going in that direction to take advantage of these novel 2D materials that they have a new physics, but with the same goal, like we want to get rid of the magnet and we want to have this type of functionalities. So this is like the context of my work. So before we start, I just want to talk about two very briefly about two concepts. One is called the Aharonov effect. Has anyone studied that in physics? Okay, guys. But okay, so that means that if you have an electron that is going very close, imagine that you have here a region that you have some electric and magnetic field inside. But outside, the electric and magnetic fields are zero. And you have an electron that is going through. If you use classical electromagnetics, you assume that the electrons shouldn't be affected by that. However, if you consider the potential around these materials, it happens, and if you do some quantum mechanics analysis, that the electron is going to get a phase that is going to acquire a phase that is going to depend on the trajectory, if the electron goes in one direction or the other. This looks kind of weird. Let me try to explain in a different way, and then I'm going to explain you in the easy way. The second way could be like how this effect has been demonstrated for photons. Before was for a single electron, and now we have for photons. And the way to explain in this second way is that if you have a system with two states, and you want to go from one state to the other one, you can do that modulating the system. For instance, with the acoustic that the system is moving around. Okay? But then we have a problem. What is the origin of the phase? That's going to depend on when you start the time of the modulation, and that's kind of arbitrary. We don't know. So we have what is called the Gauss invariance, but I don't want to enter into that. So that means that if we make this analysis from one state to the other and we come back, we're going to have some non-reciprocity in phase. After all of these things from physics, I was kind of, this looks very complicated. And then I just went to a very simple frequency mixing, and that means that if you have two signals and you multiply them together, they're going to have some phase dependence. And that means that when you're going this one frequency here and the other frequency, they can be sum, the phase is going to be the sum of these two phases, but when you are going to have the other component, the other nonlinear term, that is going to be the difference. When you are going to the other term, this is going to be one minus the other one. So the connection with all of these complicated quantum mechanics things that once you understand, they are not so, they are explained in a weird way, but at the end means that if you are modulating any system, you are just changing this phase, and you are going to have like an extra degree of phase control of your system. So it was like a parenthesis because I'm going to use that later, and I just want you to remember a little bit of this effect. So let's start about how can we control light in a non-reciprocal manner. So there is like a lot of, I think, some of the seminar before, they were discussing how to control light with metasurfaces that are very thin and they are controlled for several unit cells, like you have reflector rays. For instance, some of these structures are flying in a satellite combined with the solar panels, so they can also behave like a big antennas. You can control at the nanoscale if you have control in the different angles. There has been like a lot of work of that. For instance, Professor Salem here is very well known to establish some of the analytical approaches to analyze these types of surfaces. And very recently, people are taking these capabilities to control the direction of propagation of the light through this interface and going to time modulation. What happens if we have an interface that is changing with time? If this interface changes with time. So what people was able to do was to have light that is coming from one direction and it is converted to a different frequency, or able to control, to have one frequency conversion with some particular phase, or able to control all of the different harmonics that you are being generated, or even have a bunch of functionalities. So all of these things are pointing out to one concept, like we want to control light with these surfaces, applying not only a spatial variation of the different elements that you have, but making the system as it is moving. And that enables new options that we didn't have before. And that's the key thing that you can have. You can have any device that you are working on. So now imagine what happened if some part of the device was moving, physically moving. You can always implement that using a varactor or using any nonlinear component. And then what are the implications of that? So in my group, we were trying to understand what can we do with that. And for instance, we came up with this concept of non-reciprocal metasurfaces, where you have light that is coming, for instance, normal to this structure, and it is refracted in that direction. But then, when you are coming from this direction with that frequency, the light behaves in a different way. So for instance, if you have a reflector and you're tracking a plane, and you are able to send the information that, for instance, in a primary radar, but if that plane sends you a lot of energy to destroy your system or your receiver, all of that energy is going to be reflected somewhere else. So mathematically, and I promise this is only one of the very few equations I'm going to write, what happens is that since each of these unit cells, we can assume that it is a capacitor that is changing with time, and this could be like a simple varactor or diode that you can modulate. What happens is that this capacitor is changing with some frequencies moving, and you have some phase, and all the light that is coming here, it scatters with different frequencies and to different directions, and that's kind of complicated to analyze, but give us some basics. So what we were trying to achieve is the following. We want to go with this frequency to only one other frequency, the one that we actually want to radiate, and we want to control towards which direction we're going to send it out. And to do so, we are saying, hey, this is unit cells that are being modulated, we can control the phase of this modulation. And using the concept that I told you before about this, when you're going up or down, it's going to be plus or minus, if we control the phase of this varactor that is oscillating usually at very low frequency, megahertz, very simple, very cheap, we can engineer that this light is actually going into that direction. Or we can make it go to any direction that we want, just controlling the phase of a very low frequency. And if we want to understand this a little bit theoretically, here we have this surface. Later I'm going to show you some experiments. So if we have a light coming here, and this surface is modulated with some space and time and some gradient, we're going to reflect the energy into that direction. But what happens when the energy is coming into that direction? Exactly the same, the reciprocal one is going to go with a different angle towards the other direction. So that's the concept. What happens if we push this farther? We can change the modulation of this layer, so all the energy that is coming from this direction goes really close to the broadside. When the energy comes back, it cannot actually go like under the surface, so you're going to create here what is called surface plasmon. The energy is going to be trapped into the surface. So that means that you can engineer and control the light as you want. And then we made all of this in some simulation with the computer, and they were thinking, how can we do this in practice? This doesn't look very complicated. And then, of course, one of my students, because they are all great, they came, hey, let's modify these cells that you were working for something else. If we are able to change these unit cells and make it dynamic, this is going to work. And the initial idea that he had is like, well, you have a simple patch, energy comes here from the patch, enters through the slot, goes into this direction, is reflected back, goes up, and is radiated again. And all of this path is going to get some phase. If we are able to change the position of this path, we are going to be able to control that phase. But yeah, if you fabricate all of these things and you start changing that, mechanically, that will never work. and then say, yeah, let's just add a simple varactor over here. So we just have one of these pins, and we just connect it to a very simple varactor. It's like a capacitance that is changing, that we can change with some voltage. So we apply a very simple voltage, and then we realize that for the frequencies that they were coupling, we can control the phase as we want it. And we have a huge control of the phase. So that means that we feed this with some frequency, and we were able to go, for instance, from 9.2 to 8.6 frequencies, and we were able to control the phase. And this is exactly the same as I was discussing before. If we are able to control the phase of the very low frequency signal, this is like a picture of the prototype, this is like very low, like 500 megahertz, very low frequency, and this is like an X-band, like 10 gigahertz satellite communication frequency. So what we were doing is like only controlling the phase of the very low frequencies, we control the phase of the entire thing. That was one ingredient. The other one is like, yeah, we want that all the energy that we put in the system is going to get converted to the other frequency that we want. And playing a little bit around with the system, we managed to get over 10, 15 dBs of conversion. So all the energy that we put inside is going to the frequency that we want. So what are we doing right now in this project? So we're building an actual reflector radio metasurface that is going to have like 200 unit cells, because before we build it like a proof of concept, a single unit cell. So we know this is going to work. So now we are building the actual structure with over 200 cells. So what is going to happen is like we have this feeder, like a parabolic reflector that you have on the roof of any building. You're illuminating the structure, and we are able to send all the energy, like this is the X position along one direction, and this is a radiation pattern. But what happened in the opposite case? When the energy is coming from the same direction that it was radiated, in this case, all the energy is going to be scattered around. So what we want is like if we have some interference signal or jamming signal that want to destroy our system, we're going to scatter all the power. We are not going to focus it into the receiver, so we're going to be able to handle that jamming signal in a very nice way. We can use exactly the same system to have all the energy and focus into a single spot, and when you are radiating from the spot, it's not going to radiate. Okay, so now you are saying, yeah, this is very nice, but it looks like very complicated to design all of these type of functionalities over this structure. Well, even though these results are at very high frequency, 10 or even higher, what happens is that our control is over a modulation frequencies of a few megahertz. Those are very simple and very cheap to control. So it is very cheap and actually low loss and effect and efficient to design 50 or 200 of these cells and control light as we want. So this is like one way, and to my knowledge, like the first proof of concept to control light over a surface independently. We can control transmission and radiation. And we were interacting with beams in free space. So that was like the first project, and after we learned from that project, we were saying, yeah, but what happened with communication system like 5G, 6G, that you have these phased array antennas that are tracking you where you are? You are not actually, most of the antennas, they are not interacting with beams from free space. They are actually something that you have in your smartphone and are radiating. And in the new communication system, what it's going to have is to have some very well-defined beams that is going to be directed to any one of you. And the concept of a phased array antenna is kind of simple. You have many antennas like in a periodic arrangement, and you're controlling the phase of all of them. And then you have some interference pattern, so you can send this to one particular direction. If you control the phases of all of these antennas, then you can send it to any other direction that you want. Why is this useful? Well, for instance, all of the plane, you have radar made of this phased array antenna. You don't have to see, like, for instance, some time ago, most of these radar, they were like mechanically moving. So if you see these things that are always moving, that's a radar. But it's static, but it's mechanically moving. Here, you just change the phase, and the same structure is going to be able to track in changing time very quick. In milliseconds, probably quicker, what is going to be the direction of the beams. But again, these phased array antennas are again bounded by reciprocity. You transmit here, you receive from here. And this is what we want to break. How can we control, how can we change this structure to have a non-reciprocal phased array antenna? So my goal is to transmit the energy there and maybe receive from a different channel in a completely different direction in space. How can we do that? Well, so we came up with the possibility to build a non-reciprocal phased array antennas. So we want to have an antenna that is going to be modulated in time, as we have been discussing before, and it's going to be able to radiate with some particular phase due to the mixing of these two signals, and the phase of the radiation is going to be controlled by the phase of this modulation signal. So if we do that, and we are able to do that very efficiently, we're going to control all of the radiation pattern of this phase array instead of using the frequency that we are going to transmit, something that is a very low frequency, at megahertz, something easy, cheap, and affordable and effective. What's going to happen in reception? Well, it's going to be the opposite. We're going to receive exactly the same frequency in space, but due to the frequency mixing, this phase is going to be a down conversion. And if you remember from that we had sliced some time ago, the phase is going to be opposite. What does it mean? That the phase that you're going to receive here is going to be different, and the interference pattern that you're going to have in transmission and in reception, that's going to be completely different. If we are able to do that, we will be able to construct phased array antennas able to transmit in one direction and to receive in a completely different direction at exactly the same operation frequency. Okay, we came again, another student, great idea. How can we do that in practice? That doesn't look easy to do in practice. So we were kind of inspired by our previous project, saying, well, let's assume that we have a structure that is able to interact with the spatial wave coming from the space in this particular direction, and we have some phase change, which is very nice, one resonance, and imagine that we have another resonance when you are feeding the structure like from this direction, so you create some pattern, and you have two different resonances. And if we apply some modulation, again, we want to time modulate the system, we want to go from our guided wave to the spatial wave, and then this modulation frequency, the phase, is going to control that. And again, when we were looking at that, it was like, yes, it sounds very good, but it looks very complicated to do it. I want to do it in a very simple way. So we come up with a very simple structure, like any dipole or any patch antenna is just a half wavelength, and it resonates at a one resonant frequency. It's kind of simple. But what's going to happen with that simple structure if you feed it from both sides simultaneously? So you have your resonator, your dipole, and you excite from two sides. Well, this resistor models the coupling to free space, and you have like two resonators. If you feed out of phase between one port and the other port, you are going to excite the resonance of your dipole antenna, and all the energy is going to be radiated to free space. But if you radiate in phase, 0 and 0 phase on both sides, well, both of them, they are going to interfere in the center, and they are going to be reflected back, and the energy is not going to be radiated. So our idea was, okay, let's take any simple resonant and linear easy dipole or patch or resonant antenna, let's feed it symmetrically from two sides, and let's make this capacitor variable. If this works, we should be able to transmit and receive frequencies fully controlling the phase, and therefore we should be able to construct our phase array antennas. So we came up with something really, really simple. A patch antenna, like a dipole, and we feed it from both sides, like this. And we apply here a varactor exactly the same way as before to have some modulation. So it's like the antenna, due to the presence of the varactor, is like it's changing in time. So if we could like, mechanically it could be like an antenna that is going stronger, larger and smaller electrically. But it's like, you cannot see that, but electrically it's doing that. But it's exactly the same mechanical device. So we fabricate this and we measure that and say, let's see how it goes. So we match the antenna and we say, hey, this very well matched. We got a matching almost minus 40 dB. That was pretty good. And then I was always trying to be piggy with my students, like I tried to find, like, I didn't believe that it was working so well. So I told them, look, if you feed at this frequency with all the energy is fed, how much energy are you reflecting back from the harmonics? And then we realized that we are creating harmonics, but with very little power, minus 40, minus 50 dBs. So they were like, okay, you are not creating energy that is reflected back. So what is the energy? So we were feeding this antenna at 2.1 gigahertz, and all the energy was transmitted. This is like measurements at the broadside direction of the antenna. All the energy was transmitted at broadside, and we have like 2 dBs of loss. And I was like really skeptical because that was very little loss for something nonlinear, but I was like, okay, these measurements, I trust you. And then I went to the lab saying, okay, I want to see this. And it was working really good. And when we were in reception, we were feeding this antenna at 2.4 gigahertz, and all the energy was transferred to the guided mode with exactly a symmetrical nonlinear process. And now at this point it was like, why I'm going through all of this pain process to transmit energy at 2.4 gigahertz if any dipole can do that? Because we can control the phase. When the energy is going in transmission, those are measurements and simulation, with respect to the phase of the very low frequency, we were controlling the phase and the reception in a completely different way. So now we could control the radiation pattern in transmission and in reception independently. So once it was working, I was like, okay, let's build a very simple proof of concept phase array antenna. 2 elements. That's the simplest configuration that we can have. So we have these 2 antennas, and we feed them with 90 degrees phase difference. So what does it mean? Like, we have these 2 antennas, and when you are going to transmit, this one is going to be always have a phase of 0, and this one is going to have a phase of minus 90 plus the phase of this low frequency phase shifter. When you are receiving, this one is going to be the same, 0, but now the sign of this phase is going to be different. So they are opposite. Then we went to the anechoic chamber and measure how much power we were radiating versus the power of this phase. So when this one phase was exactly 90 degrees, the phase of this one is 0, this one is 0, they are in phase, and all the energy was radiated at broadside, at the direction perpendicular to the antenna, and we got a maximum. When this phase was 270, this one is 180, so they were out of phase. So here, the antennas were out of phase, and they didn't radiate. Well, they radiate minus 45 dB, nothing. Now we said, okay, let's understand this in reception. In reception, we got the opposite. When the phase here was 90 degrees of the modulation frequency at 300 megahertz, very little, very simple. We got minus 90, 180, so these 2 antennas were out of phase, and we measured no signal. However, we got a maximum when the phase is 270 here, so that means these 2 are receiving in phase. We then measured the entire radiation pattern, and we realized that we are able to transmit at the direction that we want, and then we receive at exactly the same direction with the same antenna 44 dBs lower of energy, and that was huge. And the fundamentals of the phase arrays holds in the same that if we just change these phases, we also measure light tunability, and we can control each of these radiation patterns independently. Why this could be useful? So now we are trying to find applications. So the first thing is that our conversion efficiency is virtually lossless. We were able to radiate all the energy because we have these two very strong modes. We are able to operate with very low frequency phase shifter. And phase shifter, they are not the best component to work with. As long as you increase in frequency, you have loss, you have a lot of problems. Those ones are operating at megahertz. You can go and buy a bunch of them for a few bucks. They are very affordable. We can control transmission and reception at the same frequency. We can deal with jamming signals. If we know that someone wants to block our device, we can just say, hey, we don't want to receive power from that direction. We can operate in electromagnetically crowded environments, like in chips, aircraft, ships, roof of buildings, or for instance, we're working about sensors that you are able to measure electromagnetic fields, but you are not disturbing the fields that you are measuring, because we have this non-reciprocal response. And this is kind of a scalable concept, so we want to apply this to any frequency across the electromagnetic spectrum. So far we have been working on metasurfaces that are moving dynamically, and we can control beams of space with a lot of freedom. We also designed these non-reciprocal phase array antennas able to direct the reception and transmission beams as we want. And our next concept is okay, maybe we can apply this concept to filter, like a standard filter. So I think the filter is, at least when I was a student, it was one of the first things that we studied, like inline filters. So you have several resonators all together, and they can couple. This is, for instance, the so-called inline coupling. So you are pumping energy from the source. This is like a very large filter for space technology, but the concept is kind of simple. You have a source, and you have several resonators that they are coupled, and then you have a load. And when you have a filter, you have some frequencies that are transmitted in one frequency band, but they are not transmitted into, you cannot go transmit in the other one. So it's like a regular filter, and all of you have many in your smartphone, on TV, everywhere, optically, infrared. So we were thinking, how can we apply this concept to have filters that are able to transmit the frequency that we want in that band, but they are not going to be able to receive anything. For instance, in the case of the laser example that I was telling you before, we are able to send that energy, but when it's going to be reflected back, it's going to be automatically attenuated without any other isolator. So we extend it, so we say, okay, the simplest way to do that is to time modulate these resonators. And then the math is a little bit convoluted, but once we got a clear picture, what happened is somehow the following. So each of these resonators in time domain, they create many harmonics in frequency. And when you are pumping the energy can go either at the next resonator, physical resonator at the same frequency, or to a different resonator at a different frequency within the same physical resonator. So we have a coupling scheme. And again, the key of these filters, non-reciprocal filters, are the phase. And when you are going from this resonator, within the same resonator, to a different frequency, the phase of this coupling is going to be different when you are going up and down due to this Aharonov bomb effect that I was mentioning you before. So this coupling is going to be positive, frequency up conversion, and this coupling, the phase, is going to be negative. So after studying all the math, I was like, yeah, let's fabricate this. This is going to work, or no. And we built like very simple microwave filters, saying like couple line couple, microstrip, low quality factor of resonator because it's this type of technology, and we apply the same Varactor technology, and then we have a bandpass filter, 4 poles, And when we were measuring after applying time modulation, we have our filtering response in this direction. We got some extra loss because we didn't consider well all the loss from the varactor, but we're gonna fix this in the next round. And when the energy is fed from the other direction, we got an isolation of over 20 dBs. And that was our first ever proof of concept of this type on a non-reciprocal bandpass filter. So now we are able to set all the energy go in one direction, but we are not able to receive that at the frequencies that we want. And again, all of that is enabled by controlling the phases employing from these varactors to modulate the resonators. And the way that you can think about is like you have any resonator that is changing physically in time as you are applying this modulation signal. And just the very short project that we just finalized is like, it was actually the idea of one of my students that he wanted to incorporate this to a simple Yagi antenna, saying, hey, we're going to have an antenna able to radiate, and then we combine the antenna with this filtering section, so we're going to be able to radiate at all frequencies in all directions, but we're not going to be able to receive any of that energy. So that was like a very a proof of concept, and here they are like a measure transmission and reception radiation pattern. We measure over 20 dBs of isolation, and more or less here in this block, we were trying to apply this time modulation phase engineering to open new venues, new roads, that hopefully they are going to pave the way to control electromagnetic wave in ways that they were unreachable before. And also, it's like we're trying to borrow concepts from other domains in order to engineer all of these devices that they have new functionalities compared to the one that we currently have. And these devices are relatively simple, or at least much simpler than I ever expected to. Well, in the last 15 minutes, I just want to make a very brief introduction to terahertz and infrared frequencies and how can we use graphene and 2D materials to control electromagnetic wave. And I just want to, okay, let me skip this part, and all of this part, just go here. Do you know the guys who discovered graphene, they got the Nobel Prize? I think it was in 2014. Do you know how they discovered graphene? Tape, and by luck. So I always, I'm teaching a course about metamaterials, and Professor Kane, the supervisor of the student, the 2 years before, he got the Ig Nobel Prize. It's like the Nobel Prize to the most absurd study, because he was able to make a frog fly, levitate with that magnet. And like the scientific community, they were saying, okay, it's very nice, very cute, but what is this for? And then 3 years later, he discovered graphene. How that happened? They were working on a different project, and they have like silicon, and they have graphite, and they have just some Scott tape. So what happened is that when you exfoliate the graphite with a simple Scott tape, you are going to take all of the graphite with you with the tape, but due to the van der Waals forces, like Casimir forces, like these forces are really, really strong at the nanoscale. They are able to attach and to get one atomic layer of graphene over the substrate. And then those guys, they were smart enough to realize that there was something new that nobody ever thought that was possible. It is one atom thick material. And they realized, looking at the microscope, that this was completely new. And that has a properties, electromagnetic properties, and electrical properties that nobody ever expected to be possible. In fact, there were like many studies saying that this configuration was not stable, that it was impossible to get that. Right now, most of the researchers are going to the periodic table and making 2D versions of every material that you can have, because there's like something new. And the problem of exfoliation is like you are doing this with a Scott tape, and you are going to create some flakes on the substrate. Then you're going to go with your microscope, and then you're going to look at that. But there is no way you can have a device, well, you can have a device, but it's out of your control. So what people are doing is a process called chemical vapor deposition that is kind of a standard now. So we can just deposit some of flakes of graphene, and under certain conditions, we can have this layer. The problem of this approach is that the quality is a little bit lower, but still is really, really good. So remember, graphene is only 1 atom thick. It's really, really, really tiny. And it's actually pretty cool. And one of the things that I like to explain why they are so important is for the fields of plasmonic. Have you ever studied anything about plasmonics? Do you ever hear about that? Well, plasmonic is really, really a big deal at optics, a very high frequency, in the visible. There, when you have any metal like gold or silver, the permittivity that they have is negative. And if you put gold on top of air, well, you have positive permittivity like the air, negative of the metal. That support a wave that is going only over the surface. It's propagating over the surface. And that's called surface plasma, polarity. So what happened? What is the deal of graphene in all of this? It's like, this depends on the metal that you are using. Gold, silver, any material that you may have. But they are only behave with negative permittivity at very high frequency, and they are very lossy. So if you want to have this type of wave at other frequencies, you cannot. And that was impossible. One of the big deal of graphene is that they behave like negative permittivity at terahertz, at infrared, the near infrared, and it opened like a new venues of opportunities to control and manipulate light that they were not possible before. And one of the major things that has enabled graphene, in addition to these surface plasmons, is that if you apply a very small DC bias, very modest, you are going to change the properties by a lot. So we're talking about a material that is 1 atom thick, that it may have a proper dimensions of a few microns, and it's able to change the properties 100, 200% by applying a 2 volts, and it's able to open, to have surface plasmons in a frequency range that they were not possible before. So now all the scientific community, me included, we are trying to find new ways to take advantage of this material for new applications. And at the end, we have like the way to do it is like, first we study how the electrons work in this 2D system, Hamiltonians, quantum physics, but then we can just model graphene using conductivity. It's only 2D. We don't need to model like a bulk material. It's just a surface. It's just an interface. Very simple to model, really simple to model, and to include into Maxwell equation. Then you can have, this is like some of the samples that we have in my laboratory, and later I'm going to show you about that. And in this animation, I want to show you why these surface plasmons are important. So if you have, this is half wavelength, for instance, at, I don't know, 1550 nanometer, a telecom wavelength. If you are supporting, if you have graphene, the surface mode supported in this layer are much, 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 much smaller. The wavelength is shrunk a lot. So here we have like 8, 7, it can go up to 100, up to 200. It's crazy. So that means that with only a few micrometer, you are able to have a device that is electrically huge, and you can control and manipulate wave as you want, make a device, make an antenna, make the processing, and then radiate, and all of that in 1 micron, and you still have empty space. Plus, it's reconfigurable. That means that if you apply a voltage between this point and this point, you are going to change all of that properties. So these are like one of the example of fabrication process that we did some time ago. We have some silicon, we pattern some gold, we put here graphene over a PMMA, one protective layer. This is called Raman, so we can, with light, with very high intensity light, and we analyze the nonlinear response of graphene to check the quality. So as a function of these peaks, with Raman spectroscopy, one can say, hey, this graphene has 1 layer, 2 layers, 3 layers. It is of good quality, it is of bad quality. And in that particular paper, we just control one graphene layer with a different one. So we want to control that one layer bias the other one without requiring some metal below, because we want to operate in transmission. So this is like, we measure this at terahertz. This is the equipment that we have in my lab at Davis, and we were able to control to modulate around 80% of the terahertz beams that they were going through at terahertz, but applying relatively, this was 40 volts. In our new samples, our aim is to do that in 1 volt, and some reports in the literature are able to do that with 0.5 volts and going lower. And this is just one of the many opportunities that graphene is enabled. And for instance, in a very recent other work that we just came out, we were trying to look at the properties of other materials. For instance, one of the most exciting one is MOS2 that have a very strong spin locking and support exciton. Excitons, they are like electron pair holes that are over this material. So what we did is like, we are coming with some unpolarized light, and we're going to excite, we're going to change that only the light that is, for instance, right-handed polarized goes in this direction, and the light that is left-handed polarized, the different polarization, is going to go to the other direction. So we just measured the photoluminescence, and we got like pretty nice results, but the idea is that just controlling the properties of a very small flake of 2D materials, we were able to control light in ways that they were not possible 10 years ago. It would be like nobody thought that it was possible. And this is just like the beginning. Like, there are so many 2D materials, so many opportunities, and to control light, to take advantage of the reconfigurability of this material, that I think that the ways that we're going to be able to make devices control light and enhance the data rate of our devices and our communication system are really boundless. I think that only imagination can find a way to stop that. So I think I'm going to finish here. I'm almost done. I have a few more other slides, but maybe that's going to be like too much. So thank you very much, and if you have any question, I'll be very happy to answer those.